This is the video for lecture 2.4 on approximate integration. And in this video, we will learn and then use several methods to approximate definite integrals to find, namely, the area under a curve or related quantities. And more importantly, and for most of the video, we'll spend some time assessing our accuracy with these approximations. So we'll see that although approximation techniques give incomplete information about the true area under a curve or some related concept, if we understand how much or how far off we could potentially be using some error estimates, we can actually fill in the rest of the picture. Let's get started. So recall from Calc 1, you learned that the definite integral of a function f of x dx from x equals a to x equals b is, in its original definition, it's the area under the curve, but this is computed by or given by the following limit. It's the limit as delta x approaches 0 of the summation from 1 to n of certain rectangular areas given by height f of xi star and width delta x, where delta x here, the lengths of each of the subintervals we divide our interval a to b into. And to compute each height of the rectangle, xi star is some number on that particular subinterval, on the ith subinterval from 1 to n, that's used to compute an approximation. That's used to compute a height in order to compute the rectangular area. If we can't take a limit, which in general for very complicated functions could be difficult or even impossible to compute, the sums on the right, just finite sums of numbers or of areas of a finite number of rectangles, are actually approximations to this area. You may have seen this in Calc 1, but a lot of what you probably remember involves the much easier to deal with definite integrals, since we have integration techniques we've developed along the way. However, if we actually make choices on each subinterval without taking a limit, we can generate an approximation and compute this using a computer. We'll do this by hand in this video, but in general, you'll learn how to code this later in the class. So the simplest way to approximate the area under the curve of a function, we'll stick with this setup for the rest of the video, is just to choose one of the endpoints of each subinterval. So let's start by choosing the left endpoint of each subinterval, and we'll use the notation capital L sub n to denote the left endpoint approximation using n rectangles or n subintervals to the definite integral, the integral from a to b of f of x dx. So without putting a limit as delta x goes to 0, this is what the approximation formula looks like. It's a summation of n different rectangular areas. And if you're intimidated by this summation notation, don't worry, we're going to do a lot of really concrete examples today where we literally just write down some finite number of rectangular areas and add them up one by one. This is just the notation that mathematicians use to denote any such summation where we're allowed to choose any function f of x to give our heights, any delta x base width, and any number of rectangles, and we'll display them from 1 to n. Similarly, we'll use the notation capital R sub n to refer to the approximation when we choose right endpoints. So the first example, we'll do this together, is to compute an L3 approximation, so left endpoint approximation of 3 rectangles of the following definite integral. After that, we'll look at a graph of the function to answer the question, does this approximation overestimate or underestimate the actual value of this integral? And of course, we can use calculus, namely the fundamental theorem of calculus, to evaluate this integral directly and know the true area under the graph of this function. So to get started, if you want to try this yourself, compute an L3 approximation. For example, if this is a review topic for you from Calc 1, then go ahead and pause the video now while I get things set up. And just to get us started, I drew the graph of y equals x squared on the picture here. And I've shown 3 different left endpoint rectangles in blue. So we can see once we add things up that the 3 areas will give some approximation to the true area under the graph from -1 to 5. We chop this up into 3 regions, and I'll compute delta x for you in a moment to get 3. But you can already start looking at the question of, is this an over or an under approximation, just once we have the graph in front of us. Let's first start by finding delta x, that's part of the formula for L3. In this case, we're always going to take the total interval, which is from -1 to 5, and chop it up into n distinct but equal sized parts. if n is 3 in this case, we want to take the total length of the interval, which is 5 minus -1, and in general it's b minus a, and divide it into n, here 3 parts. So 5 minus -1 is 6, divided by 3 gives us a base width of 2 for each rectangle. And you can see in the picture that I already drew that each rectangle will have length 2 or width 2, let's call it. And let's stay with, or let's even say base and height to keep the orientation in this picture. So next, let's compute the full L3 approximation. How do we do this? Well, there's some nasty looking Riemann summation formula with the summation symbol from 1 to 3 f of xi star and all that. But what we're really doing with that formula is saying, let's just add up 3 different rectangular areas, and each one has f of some input value along the x-axis as its height, and delta x, which we just computed is always equal to 2, as its width. So I'm actually going to immediately factor out a 2 for the width and just add up the heights, and then we'll multiply by 2 at the end. Let's compute the height of each of these rectangles. How do we do this? Well, you want to remember that f of x, the function, in this case x squared, tells you the height of each rectangle. We just need to remember the rule we're using, in this case the left endpoint rule, to tell us which value on each interval to plug into the function. So I'm actually going to write in green here the 3 left endpoints, -1, +1, and 3, that are the left endpoints of each of the subintervals of length 2, making up our full a to b interval. If we plug each of these into the function, we'll get the heights we need. So the first x value we plug in is -1, and we'll square it since we're plugging into the function x squared. Then we'll plug in +1 squared and 3 squared. And it's as simple as that. Now we've done sort of the calculus. It's not even really calculus. We're not using derivatives or integrals. But we've done the approximation setup, and we just need to compute the answer now. So this is hopefully the easy, maybe even fun part if you like to race yourself like I do. So -1 squared, that's 1, 1, and 9 inside the parentheses. So I have 9 plus 2 more is 11 times 2 is 22. Hopefully it's still okay hearing me with my dog barking at other dogs outside. Maybe she'll join us for one of these videos. So we got an approximation of 22 for the left endpoint approximation to the true area under the graph of x squared from -1 to 5. If you want to compare to the true area under this graph, you know how to find that. This is a definite integral problem. So pause the video now and compute that by hand, or use a calculator to do it quickly and just compare it to our answer 22. I'm not going to do this, but I'll leave this as an exercise. Let's get back to it. Oh, the next question, by the way, was, does L3 over or underestimate the actual value of this definite integral? If you haven't thought about this yet, pause the video now and look at your sketch, or wait a moment and I'll show you the sketch again and think about this question. So here is an actual computer generated graph of the function f of x equals x squared from a little further past our bounds we need. You can see the 3, now they're yellow, I had them blue, rectangles we use to approximate. And shaded in red is just the difference between those yellow rectangle approximations and the rest of, up to the graph of x squared. So it looks to me like, although we are undershooting, we're overshooting the graph down here by a little bit. See that the blue graph is below this red error, the amount that we're off from the true answer. We're actually undershooting by quite a bit when we go past +1. And we'll see why this is true later in the video, why this is to be expected. But the fact that this is a vast under approximation means that the whole approximation, our answer of 22, was really an under approximation. It was an underestimate to what the true value is of this definite integral. So this is going to be the main question that we ask and hopefully answer during this lecture video. How accurate is our LN or RN approximation? We can make approximations all day, but if we don't know how accurate they are, they're not really all that useful. So we're going to quantify this using some mathematical terminology, which, although it's, it's bolded in blue and it's a scary looking definition, this is actually something that should be pretty intuitive. So the error in an approximation is just the amount off that we were. In theory, we don't know what the true value of a definite integral is if we don't have integration techniques to compute it. But whatever the actual value is, the error is what we call the difference, or really the distance away from that true value we are when we compute the approximated value. So in general, we don't know what the true value is, so we cannot know what the true error is. However, we can control error by placing a bound on this error or having some theoretical guarantee that the error can be no larger than some value. We'll call it capital N for now. So this is called an error bound. Notice that this is an absolute value. So what we're really doing is saying that whatever the error is, if we're over or underestimating by some amount, it can be no bigger than n and no smaller than negative n. This is a more compact way to write this. So here's some questions to think about when determining error bounds. In what circumstances is the approximation exact? In what case do we have exactly the right answer without having to compute error, just by using these rectangular estimates? Second, what property or measurement seems to correspond to the amount of error that we see? So if we don't have an exact measurement, an exact approximation, what is really going on with the function that makes it not exact? And finally, I want you to think about this and write it down before we expand on it together. Maybe draw a picture or two. Is there a worst case scenario associated to the property or measurement in part 2 that you wrote down that gives hopefully an error bound that tells you the worst the error can be if we can control that property or measurement? This might be a little vague, so we're going to work on this together, but pause the video now if you want to think about these a little more. So moving on, here's an exercise to think about this, and I'm actually also going to leave this exercise to you. We'll come together and turn this into an actual mathematical error bound on the next slide. But the exercise here is to first draw a function for which the LN left endpoint approximation is always an overestimate. It might take a couple tries, but I want you to do this on a piece of paper. Next, once you've done the overestimate one and you observe what's going on with that, it should be a little quicker to draw a function for which ln is always an underestimate. And once you've figured out both of those, this might help you answer the question number 1 on the previous slide. What has to be true for a function to always be an exact, true of the function for the ln approximation to always be an exact estimate? Finally, tying these things into calculus, what concepts from calculus can help you describe the situations in parts A and B, and ultimately to help you relate this to our approximation of error? So I hope everyone will actually pause the video and do parts A and B for sure. We're going to talk more about parts C and D. So take this time to at least think about part of this exercise on your own. I'm going to move on now. Here's a picture that maybe you didn't draw anything that's complicated, but if you drew something close to this and have something like that dotted line hanging out, then you're on the right track. What's going on in this picture, which summarizes one way to think about the previous exercise, is that at least when we have left endpoint rules that are an under approximation, it appears that the function has to be increasing. And indeed, over each interval, we have to increase in order to create some space above the rectangle that's approximating and below the graph. That's how you have an under approximation. So the answer for, I think this was part B, how to have an underestimate, is to have an increasing function. If the function increases and decreases, then we have to break our graph up into different pieces. Now, if you did parts C and D of the previous exercise, you might have come up with something like the following. If we start by drawing a straight line out of the left endpoint on each interval, or really let's take the entire interval A to B and draw a straight line that is always lying over the graph, then this will always cap off how much possible error above the rectangle approximations we can have. And how do we get a line that lies over the graph all the time? Well, in this case, we have a function and we plug in the left endpoint into not the function itself, but the derivative of the function to find the tangent line, which is this dotted line shown here. And notice that that tangent line, in some sense, it's the closest approximation to the function we can get just using a single derivative. And in another sense, it's a good way to bound or control the error since all of the red shapes here have to stay below this line. The worst case scenario is if the graph, the solid blue, was equal to its own tangent line for some little interval, in which case this straight line would completely capture the error inside of smaller triangles. But you can see that the error is even better than that bound here. To make things more concrete, let's together formulate an error bound for Ln using our observations in that graph and using the exercise that hopefully you were able to think about. So here we go. I'm going to start by just shrinking things down. Let's zoom into a single interval. And I'm actually not going to get any more complicated than this because this will be enough for us to determine an error bound. So I've color coded things a little bit here. You'll see that just like the graph I just showed you, the graph of the function is in black. It's increasing. And if we approximate using a left endpoint approximation for at least this rectangle, the blue rectangle area is smaller than the total area under the graph. So our approximation is here. The true area under the graph is actually this blue rectangle plus this little purple curvy wedge. But just that purple wedge by itself is actually the error. It's the difference between the total area under the graph and the approximation. Another way to say this is that the blue plus the purple region equals the true area under the graph. The error is the difference between those. You can see a little bit of red peeking out here, so let me explain what's going on here. The red line here is the tangent line. And the little red area shaded in between the black curve and its tangent line is a little bit of extra error that if we include all of that triangle above the blue rectangle and up to the red line, that's sort of the worst possible overshot or overestimate we could have performed if we only knew about the tangent line and didn't know what the true y values on this curve were. So another way to say this is we can roughly sketch a curve by just drawing a tangent line over a small region that's staying pretty close to the curve. And if we use that tangent line instead of the true function, then we get a most possible or worst case scenario for error. So first of all, the approximation here, I just want to remind you, for this single rectangle is base times height of that rectangle. The height here is f of xi star, which here it's the left endpoint xi, and then the base is delta x. So that's a familiar formula. This shows up in the summation formula for the left endpoint rule. The worst case error here is really what we get when we take the area under our graph to be roughly approximated by everything under the red line. So let's add that up. Well, the rectangle is first. It's the same formula we just wrote down. This is the approximation. And if we include everything under the red line, we know this is, by the picture, this is going to be an over approximation. Well, let's write down specifically what else is left to add in to get this over approximation. Well, the remaining area to add is a triangle. So its area will be 1/2 times base times height. And the base is going to be delta x. Notice it has the same base width as the rectangle. The height, on the other hand, is a little trickier to figure out. So it's not going to involve the function since it's a triangle. It's just going to be some, we really have to figure out the length of this dotted line segment over here. So how do we figure out the height of this triangle? Well, it's formed by a line which has some slope. And in fact, that slope, since this is a tangent line, is given by the derivative of the function. So if I change one base length unit, which is a delta x, that's my run, in other words, then, sorry, actually, I should probably do this in two parts. So what is the length of this line segment? It's given by the change in y. I'm going to call that delta y for a moment, or the rise of this line. Which is governed by the following equation. So change in y over change in x will be equal to the slope, which is the derivative of the function at xi. So the slope of this line, again, is a rise over run. That's delta y over delta x. If I travel, let me make that a little cleaner. If I travel by delta x going horizontally, that's the the base of the triangle, then I should travel delta y of delta y units vertically, and that's the quantity we're interested in. So if we solve for delta y, I'm just temporarily calling it that symbol, it will be f prime xi times delta x. I'm just going to pass this to the right side and solve for delta y. And I'm going to plug that directly into the formula. So it's going to be the derivative evaluated xi times delta x. So this piece here is the height of the triangle. We also need to multiply by the base of the triangle again. Don't forget. So we have 1/2 base times height. And that actually gives us the total red area is 1/2 derivative evaluated at xi times x delta x squared. Let's rewrite this in one step just to clean things up. It's this piece plus 1/2 derivative at xi times delta x squared. Okay, so there we go. Let's turn this into an official formula for an error bound by extending this to every subinterval and every rectangle in our approximation. We're going to state this as a theorem. This is the error bound theorem for left and right endpoint approximations. We computed this, or we proved it on the last on that last example for EL, but this actually works for ER as well if you draw a similar picture. And the error bound says that if we approximate the integral from a to b of f of x dx using ln or rn approximations, and we know that the derivative f prime of x is bounded by some number s on the interval a to b, namely that the absolute values of f prime of x are bounded by that number s, then we can control the error. We will know that the error is no worse than the following bound. So it's the same bound for EL and ER, and the bound says that EL is less than or equal to that number s times b minus a squared divided by 2n. Where does this come from in our previous example? Well, the only thing that's really going on here, let me switch back and show you this for one more moment. The only thing that changed is that I wrote this for the entire interval a to b, but notice that this red arrow we wrote down is exactly, or is awfully close to that theorem that we wrote down. So the error here is equal to 1/2 times the derivative times delta x squared is really b minus a divided by n squared. That's our formula for delta x. And if you say that f prime of x can be no worse than some number s on this interval, then that's how you get the formula with s involved. So you'll see that there's a b minus a squared and an n squared in that formula. And sorry, there's a single n because we're going to add up n copies of this error bound. That's how we get the formula in the slide. So let's go back to the slide and take a look again. So here's our error formula. There's a b minus a squared coming from that delta x squared, and then one of the n's goes away since we add up n different rectangles with this bound. So here we go. This is a good error bound. It tells us that if we can compute the derivative and bound the derivative on this interval, we can tell the worst case scenario for error possible, and then that allows us to control our approximations even better. So we can fill in the missing information in that error approximation, or that approximate integration. Let's do an example to work this out together. This has 4 parts, so I'll do this in a couple steps. Suppose that we want to approximate the definite integral from 1 to 16 of square root of x dx using a left endpoint approximation. First, what bounds can we put on f prime of x, and really the absolute value of this derivative to write down the error formula from the previous slide. Next, what bound can we put on the total error for this approximation L5 using the previous slide's error bounds? And finally, maybe more interesting is if we wanted a tolerance of 1/100th or 2 decimal places of error, then how many rectangles n do we need to guarantee that our approximation is within that error tolerance? Finally, this is more of a theoretical issue or a conceptual problem that we'll talk about at the end. What would happen if we tried to integrate our function from 0 to 16 and approximate using rectangles? We can certainly do this pictorially, but if we wanted to control the error, there's going to be an issue with our previous theorem. So let's get started on this problem. I chopped it up into 4 pieces. I want to talk through each one with you. So first of all, let's actually draw the graph. This is square root of x from 1 to 16. It's always in the first quadrant. It's always above the x-axis. So we're literally just computing an area under the graph from 1 to 16 here. There's no signed area business. We can chop this up into rectangles. I'm not going to bother drawing it because in this problem, we just want to control and understand the error involved in some approximation. So part A asks us to put bounds on the size of the derivative of this function over this interval. So the first thing we need to do is actually compute f prime of x. This is a power rule problem. Square root of x has derivative 1 over 2 times square root of x. I'm just going to write it this way because in a moment it will be easier to deal with. And that moment is now. If we plug in the 2 endpoints, 1 and 16, let's see what happens to the derivative. And because the function not only is increasing over this entire interval, its derivative is actually decreasing over the entire interval. I'm going to write that down for us. F prime of x decreases over the entire interval 1 to 16. You can use another derivative, find the second derivative, which is the derivative of this function, 1 over 2 root x, to prove that. But you can also just observe that plugging in larger numbers to the denominator makes the whole fraction smaller. In any case, knowing that this decreases, one of the endpoints will have the largest possible f prime value and the other will have the smallest possible. So let's just figure out what those are. If I plug in x equals 1, because the derivative decreases, that should have the largest one. So I'll fill it in over here on the right. Plugging in x equals 1 gives 1/2 for the size of the derivative. Whereas plugging in 16, x equals 16, gives me 1/8 for the size of the derivative. You can think of this as asking, well, if we drew a tangent line here or here, which one would give the worst possible overestimate? And it's clearly the steeper line of the two. And if you're not quite sure about that, I encourage you to draw some pictures to understand this better. Sketch out this graph that I've shown you, and then try experimenting with different tangent lines to see which gives worst approximations. Why we're asking for the worst approximation is because we may not be able to find the true value of this interval, but we want to know what's the worst case scenario so we can aim within a certain range of values. And we know with certainty then that our approximation will be correct within that tolerance. So now we have a bound. We have 2 bounds on f prime of x, but we'll mostly be interested in the upper bound because remember that according to the theorem, the left endpoint approximation L5 has error EL that's bounded in absolute value by the formula S times b minus a squared divided by 2n, where here S is a bound on the first derivative of the function. In this case, we'll use an upper bound. F prime of x is always less than or equal to 1/2. It's the largest that the derivative slope can be. Let's plug things into this formula. S is 1/2. I'm taking that from up here. B minus a, let's see, we were going from 1 to 16. So this is 16 minus 1 quantity squared. And then 2 times the number of rectangles. L5 has, it's 5 rectangles, so the denominator will be 10. Let's work this out quickly to see what the error tolerance or what the error bound is here. The worst case scenario, let's see, 15 squared is 225. I have 225. I'll move the 2 down. 4 times 5 is 20. Actually, maybe it'd be a little easier if we divide by 2 first. So 225 divided by 2 is, let's see, 112.5 divided by 10, which I'll just move the decimal place. This is 11.25. So here is our worst case error, which, okay, maybe you think 11 is a small number. It's much smaller than 225. But this is actually the number of units that we could possibly be off from the true area under the graph of this function from 1 to 16. So that's terrible. That's 2 digits worth of units that we could potentially be off by. But we only used 5 rectangles. So maybe, we were a little lazy. We only computed 5 rectangular areas. We shouldn't expect to get that tight and close to the answer. So 11.25 is the worst case scenario. If we're working on large scales and we only need to be within 100 units of the real answer, this is great because we're only potentially under 12 units off. But that's the story so far. And we actually know it would have to be, the approximation with left endpoints has to be an overestimate, again, because the function is increasing on this interval. So the true value that we get using the tangent line would be no more than 11.25 units off. So we could subtract from that and get a pretty reasonable estimate here. Okay, let's move on to the next part. So if instead we get to choose how many rectangles we use in our approximation, but we have an error tolerance or an error threshold we need to be restricted by, or we need to fall within, let's say 2 decimal places or 1/100th, let's figure out how many rectangles n we need to use to guarantee that this error bound falls within the designated tolerance of values. So again, we have the same s showing up in this formula. So the error bound over here is telling us what the worst case scenario for error is. And if the worst case scenario for error is less than or equal to 1/100th, then we're good to go no matter what. So let's solve this whole expression for n. First of all, I'm going to plug in s, b, and a. I don't know what n is yet. We need to find n. So s was 1/2 from 2 parts ago. B minus a was 16 minus 1 squared, that was 225. And then 2 times n, we don't know n yet, is less than or equal to 1/100th. I'm going to solve for n, so I'm going to multiply by 2n and multiply by 100 on the 2 different sides. If I multiply by 100, I'll get 1/2 times 225 times 100. And I'm not multiplying these out yet because I'll do it in a moment. And then on the right, I'll get just a 2n. So I'm not so good at multiplying, I could divide a 2 and get a 25 and multiply that by 225. If you're comfortable doing that way, that would be good. But I think what I want to do is multiply the whole thing through by 100 first. This can be 22500. And then I'll divide by 4. So I'm going to divide by 2 and then I'm going to divide by another 2. Let's say what this is. I'm actually going to cheat and just use my computer, but you can. 4 is 5625. This is the sort of thing that you could use a calculator on. 625. I got that right. 5625. Good. Okay. So this means, well, n is greater than or equal to 5625. So if we use at least 5,625 rectangles, we're guaranteed to be within 1/100th of the true area under this curve. So that's a lot of rectangles. The takeaway here is the square root function kind of stinks when it comes to rectangular approximations. We'll talk about different ways to handle this in a couple slides, but first, let's answer the final question. Oh, there's a bit of a hint what's coming next. What problem would happen if we tried to bound the error of an ln, a left endpoint approximation, to the integral from 0 to 16 of the same function, and how might you fix this? So I'm actually going to leave this to you to work out, but I want to give you a slight hint again that the derivative of this function is 1 over 2 root x. How will that go wrong when we try to control the error or bound the error above by some value like we did in the previous couple examples, if the derivative is this? Let's get back to our exploration of different approximation techniques. And as we just saw, the square root function is not so good at being approximated by left endpoints. You could try a right endpoint approximation. The story will be the same. The function is just moving or changing at a much different rate than straight lines, which are the straight lines are both the tops of our rectangles, those are horizontal lines, and our tangent line worst case scenario error bounds are straight lines, giving us those top triangles. The square root function just behaves differently than lines and rectangles and triangles, so we need to do something else. So how can we make our approximation less sensitive to slope is really the question that we can get at here. When our function increases or decreases rapidly, this is especially the scenario when our error bounds are large. In the last instance, the square root function has its largest increases when we have low x values. The derivative gets, again, the derivative decreases as we move to the right on the number line. But when we're in that range, from 1 to 16 was pretty small x values, can we find a way of approximating things that are a little more resilient to these large changes in slope? Or large changes in quantity, so the slope is large. So we're going to introduce the following approximation technique. You may have learned this in Calc 1 as well, but I'll state it fresh here. So the MN approximation is called the midpoint approximation. Instead of using left or right endpoints, we'll choose the x value xi star to plug into the summation formula, just to be the midpoint of these two endpoints. We'll plug that into the function to get a height of the rectangle. And the general formula looks the same. It's the sum from 1 to n of f of xi star delta x. But here we'll plug in xi star to be the midpoint. And the best way to find a midpoint is using the following. Oops, sorry, that's a different slide. The best way to find a midpoint is to add together the 2 points and then divide by 2. So if you add together 2 points and divide by 2, then you will get the halfway point between those. And that's just what you're plugging into the function. Another way to approximate, we'll do an example of both of these in just a moment, is let's abandon rectangles with our horizontal tops to them and use straight lines that hug the graph a little closer. This is going to work a lot better for something like the square root function. And the name of the game here is trapezoids. So if we have a trapezoid, we can compute its area quite easily using a couple different formulas. The one that we'll use here looks like this. It'll be 1/2 sum of the two bases times the height. And if you work out what that means for the interval values x1 through xn plus 1 along the x-axis and the heights coming from function evaluations, then the trapezoid rule Tn, using n different trapezoids approximating the area under this function, will be given by the summation from 1 to n of the following trapezoidal areas. 1/2 times the height, which is the sum of fxi and fxi plus 1, times the base, which is the same delta x. We use the same base width as with our rectangles. Another way to say this is if we want to compute a trapezoidal approximation, we can take the average of the left and right endpoint approximations. And you can see this geometrically if you draw the over and underestimates using rectangles for each of these trapezoids. Take their average, and that's going to give you the trapezoidal estimate. You can see in this picture here is a much closer approximation to the curve square root of x, which may not always be true. Trapezoids aren't strictly always better, but we'll see that their error bounds are, in general, have the potential to be better or produce less error in the approximation. So let's do this one together. Let's compute the 3 rectangle midpoint approximation of that same integral that we started with today. The function is x squared. If you want to try this on your own, it's a good time to pause the video. I'll show you the sketch that we started with last time, except now I've drawn rectangles whose heights are given by midpoints of each of these intervals of width 2. So just to remind you, our delta x was 2, we computed above. It's the total interval divided by 3 rectangles. M3 here is going to be exactly like we did for L3 and R3 previously, or we only computed L3 together. Let's just write down delta x times the sum of all of the heights of the rectangles. And we can see them drawn on the graph. All we have to do is figure out what the midpoint values are. They're 0, 2, and 4. Plug those into the function x squared and then add up the output values. So we're going to square 0. You can see the height of that rectangle is 0 in the picture. Square 2 and square 4. Add these up and multiply by 2 for the base width of each rectangle. So 0 plus 4 plus 16, that gives me 20 times 2 is 40. So our approximation to this same function over the same interval, the area under the function is 40. And you can go back and compare that to what we got with L3. And if you want, try R3 using right endpoints to compare all of these together. Let's do the next one together right away. This will be on the next slide, but this is what the problem shows. We can approximate trapezoidal, or we can approximate using the trapezoidal areas instead of rectangles using the summation formula that I've copied for us here. And if we have a table of values for function, it's actually pretty quick to read off and write down each of these trapezoidal areas. We just need to add up the two different heights of the endpoints of each subinterval lying along the bottom of the trapezoid, and then we'll multiply by delta x and divide by 2 for the 1/2 base times height, or 1/2 sum of the bases times height computation. So delta x here, if we're going to use a T3 approximation and the interval runs from 2 to 14, that has length 14 minus 2, or 12, dividing it into 3 chunks. So each chunk will have length delta x equals 4. I'm going to take 1/2 times delta x, which is 4 over 2 is 2, and I'm going to pull that all the way out front and just add up each of the, let's put this in square brackets for the whole summation. I'm going to add up the sum of the two endpoints of each interval. And just to be clear, because we're using delta x, or width of trapezoid, to be 4, I'm going to put a little tick under all of the endpoints we're using. There are 5 of them because they'll form 4 subintervals. So for each, as we shift from trapezoid to trapezoid, I'm just going to take left plus right values, but we're going to plug them into the function. We can read those off the second line of the table. So f of the first left endpoint is, so that the x value is 0, but the output value is 2. Oh, you know what? Sorry. I didn't realize the table started too early. So we're going from 2 to 14. So here's the left and right endpoints. We want to use 3 subintervals, so there should be 4 different endpoints we use. Apologize for that confusion. So we're going to start at x equals 2, that's the leftmost value here, and plug f of 2, which is 5, and then f of 6 is the next endpoint. It's going to be 4. If we move on to the next trapezoid, now x equals 6 is the left endpoint, so its height is 4, plus the next endpoint's height is 8. I'm just reading off these, sorry, I missed one. These 4 with tick marks under them. The next trapezoid, the last trapezoid, has left endpoint with height 8 and right endpoint 14 with height 4. So if we add all of these up and multiply by 2, let's do this quickly. So 5 plus 4 is 9, plus 12 is 21, plus another 12 is 33 times 2 is 66. So our T3 approximation to whatever function this is, where we only have these tables of values, is computable, and the answer is 66. Now, it'll be an interesting question how far off from the true answer this is. But without more information, it's hard to say. Notice that I reused, I'm going to highlight this a little bit, I reused my inner endpoints, the ones that showed up in multiple trapezoids. And a nice way to, sometimes a nice way to rewrite this formula is as follows. So I can sum from, so let's do it this way. Let's pull out our delta x over 2 all the way up front, because that shows up in every term. If we plug in the left endpoint, that only shows up in a single trapezoid, f of a. And then if we start at I equals 2, that said 2 and I wrote 1, so I'm going to change that. Start at 2 and then end 1 short of the right endpoint. We'll go from 2 to n minus 1 of f of xi. And then at the end, if we add in, and sorry, I also made another mistake. The point is we use each of these twice, 2 times f of xi, and then at the end we'll add just a single right endpoint. It only shows up once. This is sometimes a little faster to compute, so I don't have to add up 2 different heights for every trapezoid. I'm just going to add up every endpoint, or every tick mark, every subinterval endpoint some number of times, and just compute it that way. So you're only using each height once this way. You can rewrite this in a couple other ways. If you distribute the delta x over 2, some things change, but this is a nice way to think about it. Okay, so we'll get to error bounds in a moment. Let's go back and look at the slides. By the way, here's a picture of what happens with midpoints, and there's a widget on the online version of the textbook that you can play with and change how we subdivide and if we choose midpoints or other points along the interval. So theoretically, we could choose every input value to compute the height, at least with rectangles, to be 1/3 of the way along the interval, or 8/10 of the way along the interval, or some sort of scheme like that. And that could change how good of an approximation we get depending on what the function looks like. I'm not going to derive these like we did for the left and right endpoint error bounds, but if you work through the same kind of detail as we did for left and right endpoints and seeing if the function is increasing or decreasing, it'll turn out you actually only need to know if the function is concave up or concave down when it comes to the trapezoid and midpoint rules. This is something to really try to play around with yourself and just draw one rectangle or one midpoint rectangle or one trapezoid at a time and see how concavity changes things. But the following error bounds hold. So let's let ET and EM be the symbols for the error bounds using the trapezoid and midpoint approximations of some definite interval. And if we know that the second derivative f double prime of x is bounded by some number k on our interval from a to b, then the theorem says that the worst case error for the trapezoid rule error bound is that number k times b minus a cubed over 12n squared. And there's a different formula for the EM, the midpoint error bound. The worst case scenario for our error in our approximation using midpoints is that same number k, bounding the second derivative, times b minus a cubed over 24n squared. So you can see in general, the denominator is bigger. The total amount of error with the midpoint rule is actually expected to be less than the trapezoid rule. I want to point something out though, and this will be a couple slides later as a reminder, that just because we have an error bound telling us the worst case scenario, this does not mean that the true error is always lower for midpoint approximations versus trapezoid approximations. In particular, if you compute something that is awfully close to the midpoint rectangle, just if you draw the graph of the function this way and make it happen, then the midpoint error approximation will be, the error will be really small in that case. Whereas with the trapezoid, it might have some hanging over pieces. And you can try to draw these to imagine it happening. But that's just a reminder that error bounds are not true error. So here's a couple of remarks about all of this, then we'll wrap things up with one more example. The maximum error in general tends to be smaller when the function has less curvature, meaning it's closer to a straight line. We're using straight lines to approximate things. So if our function looks like a straight line, then the error is smaller. In general, and this is going back to Riemann summation, if we increase the number of rectangles or trapezoids, or in general, the number of subintervals we're approximating with, the error also goes down. This is reflected in the fact that the true value of the integral is equal to the limit as the base width delta x goes to 0. The only way to fit in more the only way to have a smaller width rectangle is to fit more of them, so n has to go up. But algebraically, this is also reflected in all of these error bound formulas having n in the denominator. So if n increases, the error gets smaller. Number 3 just kind of recaps what I said a moment ago. The expectation is that the midpoint rule is producing about half the error as the trapezoid rule, but in general, we could have special situations where that's not the case. And in general, what's even more interesting is that as n, the number of rectangles or trapezoids, increases, mn and tn, the error is shrinking much more rapidly than for ln and rn. I'm not going to skip back, but the denominators for et and em have an n squared term. So if I increase n, the denominator gets larger much faster than with the rectangular endpoint estimates that only had a 2n in the denominator. This is why we say that the midpoint and trapezoid rules are converging faster to the true solution. So let's do one more practice problem together using the midpoint approximation, using that error bound that we just developed. So let's go back to our favorite, well, maybe not our favorite, but our well-studied function in this video, square root of x, from 1 to 16. And let's take a look at the error bound using a midpoint approximation. And we want to decide how many rectangles with midpoint rule used we have to use in order to guarantee that our error tolerance is smaller than 1/1000. So let's be even more aggressive and ask for 3 decimal places of accuracy versus 2 before. If you rewind in the video where you had written it down, we needed something like 5,625 rectangles to get within 2 decimal places. Let's see how many midpoint rectangles are needed for 3 decimal places of accuracy. So the error bound for EM here is given by K times B minus A cubed over 24N squared, where K is some numerical bound on the second derivative of the function. I'll remind you that the first derivative was 1 over 2 root x. And let's compute the second derivative. The second derivative is actually going to be negative 1 over 4 times x to the 3 halves, 1 over x to the 3 halves. So I'm going to write this all as one fraction since we'll need it in a moment. Negative 1 over 4 x to the 3 halves. So the second derivative is negative. We can see this in the graph. I'm not going to redraw the function, but it's concave down over the entire region from 1 to 16. And any x values we plug in here will give a negative second derivative value. We're going to need our absolute values here, in other words. So on the interval from positive 1 to positive 16, let's bound the absolute values of the second derivative over this interval. Notice again that the second derivative, these are negative values, and if we make the denominator smaller, this whole fraction is always increasing. I know that takes a moment to parse. If there was no negative sign, this fraction would be decreasing. We think of this as increasing up to 0 from some potentially larger negative numbers. So what's going on? The function's always increasing, so the smallest value that f double prime can have over the interval is when we're at the left endpoint. So left hand point of 1, if I plug that in, gives negative 1/4. That's the smallest the negative second derivative can be. So negative 1/4 is the furthest from 0 that will be, and that means it's the largest in absolute value the second derivative can get. So that's already our error bound. Let's just plug in 16 to be double sure. If I plug in 16 and take its square root, I'll get 4 raised to the 3 with another 4. That's really 4 raised to the 4. Oh, let's see, that's 2 raised to the 8, which is 32. So the worst, or really, I mean, the best in this case, but worst we can do is negative 1/32. And that means the absolute value has to be at least 1/32. So here's our error bound. Here's our bound on the second derivative. Let's go use our formula for the error bound of EM to finish things off. And then we'll have a couple questions to finish our discussion together. So K here we see is 1/4, because that's the worst case scenario for values of the second derivative. That's the worst the concavity can get. So if I have 1/4 here, B minus A is still 225. That's 16 minus 1 squared. Here I have 24N squared, and I want this to be no worse than 1/1000th. Again, we want to solve for n squared. So I'm just going to do this in a single step. Let's push everything but the n stuff to the left, and I'll have, let's see, I'll have 225 times 1,000. There's a 4, there's a 24. That's less than or equal to n squared. I'll tell you what that number is. So 225. Well, I'm going to simplify in one step. If I divide 1,000 by 4, that's going to give me 225. So I really have 225 squared over 24. I'm going to take the square root of this to get my bound on n. That's going to give me 225 over, let's see, 24 square root. That's not a perfect square, but it's close to 1. But let's see, that's 4 times 6. So I'll get 2 times square root of 6. That's going to be the lowest that n can be, but we want to use some integer number of rectangles in this case. So let's actually compute what this is as a decimal. 225 over 2 times square root of 6. That's, I didn't install. One moment. There's a different calculator. 225 over 2 times square root is approximately 45.93. So whatever this fraction is, it's about 45.93. N has to be at least as big as that, and it has to be an integer. That's the number of rectangles we'll use. So N has to be at least 46. So if we use 46 rectangles with the midpoint rule, we'll be within 3 decimal places. This illustrates how much more powerful and how much quicker the midpoint rule converges to the true answer and decreases our amount of error than the left or right endpoint rules. So I have a couple of recap questions to finish things off. And then I'll let you go compute error bounds as much as you want. Here's some summary questions. How do we define error? You'll look at the slide, it's probably slide 3 when we defined error in the first place, but I want you to think about what it means to define the error in approximation. What does the first derivative of a function tell you about the error in using a left or a right-hand approximation of the definite integral? We talked about the left endpoint approximation, so think about the right approximation as well. As the number of subintervals gets large, which approximation or which potentially multiple approximation techniques converge the quickest to the actual value of the area under the function? And finally, 4, we talked about this a little bit out loud. Under what situation is a midpoint approximation preferable to a trapezoid approximation? And when would a trapezoid be preferable? There's a couple of questions that I'll leave as exercises for you. So here's question 28 from the textbook. And here's question 30. And you can find these on the slides again. Okay, thanks for tuning in, and I'll see you next time.